The COVID-19 pandemic has drastically increased the importance of online classes and courses, and this may be the case even after the pandemic due to its flexibility. But one difficulty in such convenient learning experiences is the absence or lack of nonverbal feedback from learners. Experienced teachers may intentionally or unintentionally check the learners' states and may give some quizzes if they look bored or add some more explanation to reinforce their understanding. This adaptivity cannot be offered in an online and real-time classroom as video feeds from learners are often unavailable, or it may be hard to see how they are engaged in the class or course solely from video feeds. A potential remedy is to use recent AI technologies to assess learners' disengagement from individual video feeds. By disengagement, we mean any mental states of a learner like distracted, bored, etc., which teachers consider the learner as not engaged in the course. Here we show some example frames from a video recording of a learner who looks engaged in the learning session at first. However, after a while, he closes his eyes. This time, he actually is not sleeping and is engaged with tilting his neck to the side. But eventually, he started to massage his eyes, perhaps, because he was bored with the learning session. We want to design a model that can automatically detect such disengagement states of learners. Of course, this technical support is not as good as experienced teachers can do, but it still offers additional flexibility in designing a lecture. There are some attempts to predict learners' disengagement from various sensors. Some works use biometric sensors, like AIED, heart rate sensors, and eye trackers. Vision-based approaches may be more convenient as we can use laptop PCs with built-in cameras or ordinary webcams, and cameras are less invasive. Features related to facial expressions have been used in these attempts. We employ a vision-based approach for users' convenience and deployability. In the course of this research, we found that disengagement is tough to model with machine learning techniques. It is a highly abstract concept, and behavioral cues exhibited by a learner are visually different from learner to learner and from time to time. This inconsistency is a severe problem because this means the supervision is inconsistent. In order to alleviate this difficulty in modeling disengagement, though indirectly, we employ a multitask learning approach, in which we also predict more concrete and visually consistent behavioral cues, such as strange eye movement, presence of facial expressions, yawning, and body movement, that seem to be relevant to disengagement. This provides some more supervision in modeling disengagement through the correlation with it. We implemented a deep neural network model shown here to tackle the disengagement detection task. Given a video recording, we use a sliding window to spot a temporal segment of interest and feed the frames in the window into the model. We use the popular fast-slow network as our basis, which has slow and fast pathways. The slow pathway model longer temporal dependency by resampling the frames. Meanwhile, the fast pathway suits to model quick motion. The slow and fast pathways in our model cover 2.17 seconds and 0.57 seconds, respectively. Therefore, the former is suitable to handle the presence of facial expressions and yawning, which typically last longer, while the latter works well for strange eye movements or body movements, which are usually very quick. For multitask learning to incorporate supervision signals from different behavioral cues, our model consists of a single backbone to compute features and respective classifiers on top of it so that it can make multiple predictions of other behavioral cues simultaneously and model the correlation among the cues in the backbone. Please refer to our paper for more details. We used our in-house dataset for evaluation. This dataset contains a recording of learners' face while they were reading some text in a reading and recall test session. After IRB approval, we collected videos from 26 participants, resulting in 1,560 videos in total. During these recording sessions, some parts of the participant's face are occasionally occluded by our equipment. Also, the participants need to use the keyboard to proceed to the next block of text to continue reading. These events change the appearance of the participant's face a lot and may affect the model's performance. We thus additionally annotated these occasional events in each video. We annotated all videos with the help of 4 in-house annotators. After the training phase, at least 3 annotators out of 4 annotated a single recording. The table here shows the statistics of our dataset. We can see that it's relatively imbalanced. We got many strange eye and body motion labels, while yawing is rare. We employed 8-fold cross-validation to evaluate our model, where each fold consists of 3 to 4 participants, and used the area under the precision recall curve as our performance metric. The average score over the 8 folds is reported. This table shows our ablation study over different configurations of the model. Here we focus on comparing multi-task training with all behavioral cues and single-task training only with disengagement labels. The performance of disengagement prediction improves when the model is trained together, indicating the correlation among the behavioral cues actually helps to model high-level semantics of disengagement. Here we show a comparison with existing network architectures. We evaluated the original slow-fast network, or SF, without minor modifications that we applied to it. Please refer to our papers for the details of the modifications. We also evaluated the very popular ResNet architecture, referred to as 2D ResNet, and its 3D convolution variant, 3D ResNet. For 2D ResNet, we only used the center frame in the sliding window. 3D ResNet has much more trainable parameters, but we halved the filter sizes for a fair comparison. As a result, 3D ResNet has 11 million learnable parameters, while our model and SF have 9 million. We trained all these models with multitask learning. The graph shows the AUC-PR scores for these 4 models. Our model outperformed all other models, although the gain between ours and SF is marginal. 2D ResNet, which does not model the temporal dependency, in most cases gives the lowest scores. This result tells the importance of modeling temporal dependency for disengagement detection. These results are only some aspects of the set of our experiments. We also compared different network architectures and explored the temporal dependency in each behavioral cue. Here are the take-homes. We showed that a neural network could predict disengagement with the AUC of 0.7 when the model is trained in a multitask manner with supposedly relevant behavioral cues. Our model is deployable on a laptop with a built-in webcam. This opens up the potential to apply this technique to real scenarios. Our experiment only adopted a single learning task, and the applicability of the technique to a broader range of learning scenarios is not explored. We want to investigate this direction further. Exploring the acceptability of this type of technique is another interesting and necessary research direction. Recording the behavior during online learning is not pleasant for learners. We want to study when this is acceptable regarding technical aspects, like where the captured video is processed, either client-side or server-side, and returns provided by the technology. Thank you for your attention.